In the video number 11 in the Foundations of Computational Economics course, we'll look in depth into the binary search algorithm that we measured the speed of in the video 9. So, binary search algorithm is a member of the class of the divide and conquer algorithms, the main idea of which is to divide a big problem into much smaller and preferably equal-sized subproblems, and then solve each of them, or conquer, and that can be done recursively often, and finally combine the solutions of the subproblems together. So let's look at the very simple example. Imagine that we want to sum a list, and let's do it in this divide and conquer type of way. So let's first run this. I'm expecting an output, so I guess I should just print this. And nothing is returned, of course, because we are not returning anything from the function. The L is going to be a list. So first step of divide and conquer is to separate this list, this problem, summing up the elements of the list, into subproblems of preferably equal size. So let's first try to find the middle of this list. So we'll take the length of the list and divide it in the integer way in half. Okay, and then we can say that the sum of this list will be the sum of relative first half and the second half of the list. So we will call the same function, we will call itself with the halves of the list. So what's the half of the first half of the list? Well, that's all the elements up to j, right? That we're using slicing here. And the second half of the list are all the elements from j all the way to the end. And that's about it. So let's try to run this one. Oh, it's taking long. And we get a problem, right? Maximum recursion depth exceeded. We saw that recently in the previous video. Yes, and why is that? Why is that? As a matter of fact, let me give you some 10 seconds to think about it. All right, so the function is calling itself without ending infinitely. How do we provide an ending? Well, we have to stop this recursion somewhere, and we can say that we can check on the length of the list up in front, and if the length is, for example, 1, then we can stop, right? What we return. What's the sum of the list with only one element? Well, that's basically the value of that element. So we can return the value of the element. Let's look here. Of course, this is an assignment operator, not the quality check. And now we should do it this way. We still get a problem. Unsupported operand type for plus non-type and non-type. We forgot to return the sum of the list, because now we're returning nothing, and then of course nothing in the recursive return from the recursive call is added to nothing returned from the other recursive call. So we should actually return the sum here. And there we are. The sum of this list from 0 to 16 seems to be 120. Let's make it a little bit more clear. So let's just print a whole bunch of things. So let's see here. Let's print the inputs, right? Let's print the inputs. Let's do the following thing. Let's print the following: dividing list, and we'll give it the full list into this part, and this part. And I'm using the Python way of printing here again, and these are placeholders for whatever variables there will appear there. So I'll give it the whole list and then the two parts. so that we see that the list is being divided into some parts. And then let's print here, returning the sum of a particular list equals a particular number. So what's the list here? Format, and we'll give it the list that was given to this function, okay? And the number, which is just the sum. Okay, we get a lot of output here. So let's start with a small example first. Let's just sum up a list like this. All right. Oh, I meant to press Shift-Enter to run. And let's see what's happening. So first the function is called, right? It finds the middle of the list, and then it says that it's dividing the list of 1, 2, 6, 5, 2 into two lists, 1, 2, and 6, 5, 2. Right, we are setting j as an integer division of the length 5 over 2, so it's going to be 2. So the first list has 2 elements, the second half has 3 elements. And then see, it calls itself, but with a different list, with the first half. And so it divides the 1 and 2 into 1 and 2. And then it calls itself recursively again, and only exits over here. So if we put a print statement here as well, and say sum of list of one element is, and put that element, which is also a sum, here, and run it this way. So okay, so we're dividing on the second step, on the second call, we are dividing the list of 2 elements into single element lists, and calling the same function twice again, but it just returns 1 and 2. Okay, and then we are returning, once this is done, we are returning the sum of this first half in the first division here is 3, and then we are going to the second half, second call over here, and that is again divided into 2 parts. And for the first one, the result is returned immediately. For the second half, 5 and 2, the list is split further, and then the results are returned. And then, as it comes back here into this call, it prints the result as the sum of this list, and then finally comes back to this call, which one? This one, and returns the sum of this list, which is now composed from 7 and this 5 and this 7, and then finally comes back to this call, the initial call, where 13 is added to 3, and we get our answer. And as you can see here, we are constantly dividing the list into 2 parts and calculating different sums separately in recursive calls. So going back to the bigger example, you can see that this list is divided into parts here, and then the process goes pretty much in the same way as for this small example. I wanted to scroll this, giving the answer of 122. Now, it's definitely not clear that this is the best way to sum the elements of the list, but it is, however, a good illustration of the divide and conquer algorithm ideas. And as we know, they have good properties in the terms of computation. Oh, let's run some tests before talking about the computational complexity again. This is another implementation of the same algorithm, which I've written previously. Okay, as you remember, the complexity of this binary search, and as a matter of fact, any divide and conquer algorithm is or rests on the idea that by dividing problem into subsections, we're actually dividing the work that is needed. And going back to the previous video, we know that the complexity can be calculated in the following way. As we go down the list, we're dividing the work into, say, B branches every time. And so by the time we are at the lowest level, we have divided the, let me write this, we have divided the total work, the size of the problem of n, over b to the x, where x is the number of levels. This is x. And by the time we get down to the very bottom of this tree, or to the leaf, the level of the leaves, then we have this equation, and from this it follows that log n. My pen is not working very well. Log n equals x times log b, and therefore x is a big O of log n. Okay, let's leave it here. But that's the idea of the divide and conquer algorithms. The other many very important algorithms that are used every day actually are based on this idea. So, for example, quicksort and merge sort. Quicksort being the typical, the very standard algorithm for sorting all sorts of things in all sorts of programs. The fast Fourier transform is based on this, and as you can see, fast multiplication, very fundamental algorithms are using the idea of divide and conquer. So let's go back to the binary search, and let's code up this function, this algorithm. So remember that the input is a sorted list of numbers, and we are given a value to be found on this list. What should we do? The algorithm goes in these steps. We find the middle point of the list of numbers, similar to what we just did, and then we compare the value that we need to find with the value in the middle of this list. And that's how we decide whether we should reduce the area of the search to the upper half of the lower half of the list. Let's do it here. So we are given a list, and by default it's just 0 and 1, and the value of 0. I should write a docstring if it's not here. Binary search of val in the given list. Okay, so we need to keep track of the indices of the current region of search, so current list that we're working with. And by the way, I'm going to write this not as a recursive function, but just using loops. So I want to call my the indices for the ends of the current search area as I1 and I2, and this will be initialized to 0 and length of list minus 1. These are the indices, so they are base 0. And then J is going to be my pivot point, which is just the middle between the current boundaries. And this should all be integers, so I'm using integer division. All right, and here's my loop. While something, I don't know yet what the condition will be, what should we check? We should check whether whether the element of the list at the jth place is larger than the value that we want to check, that we want to find. So if the element of the list in the middle is greater than the value, then we have to shift our attention to the lower bottom of the list, and that means that we need to update the I2, the upper half, to j, right? Else, if the value of the list is below, if the element of the list index j, the middle element of the list is below the value, then we need to shift our attention to the upper half of the list, and that's achieved by moving the lower bound of the region of interest to j. And then to get ready for the next iteration of the algorithm, let's copy this line again. Oh, by the way, this I1, I3, no, that's a bug. That should be I2. So copy this here, and then we continue the list until what? Well, until the list of j equals, or doesn't equal the value. Let's try this. Give it a list. The list must be sorted now. And the value must be in the list. So maybe it's 6. And I want to print this. As always, I forget to output anything. So let's return. What should this binary search return? It should return the index, right? We know the value that we're looking for. We need the index where this value is. So the index should actually be j, right? Because the loop here, the loop will go on and on until the element of the list equals actually the value that we're looking for. And so here we are. So 6th is the first element, or the element with index 1. That's the second element. If I say 34, for example, that's this element. What about if I say 67? Oh, it doesn't work. Interestingly. So what happens if the value that I'm looking for happens to be at the very end of the list, or maybe the very beginning? We're also not getting anything. What's going on? We're probably in the infinite loop. Yeah, this hourglass over here, the hourglass over here shows us that the Jupyter Notebook is working hard, but not getting anywhere. We're in the infinite loop probably. So I'll interrupt the kernel. And let's try to maybe restart the kernel. So we are restarting the Python that runs on the background here. And let's try to investigate what's going on. I'd like to make some diagnostic output. Maybe this should be done under an additional argument, so we don't get this output every time. So this is only when we want to run this code in the verbose mode. List is let's print the list. Let's print the value to find. File. And I'm sorry, what am I doing here? And as we go through, let's print the current state of the search. So where should this happen? So I want to print the current area of the search that we are checking. So probably it should be here. If we are right at the first let's see. If we are right at the if the value that we're looking for is right in the middle of the list, then we still probably want to get some output. Well, let's put it here. Found the value and then index. Like so. Okay, so even if we find it right away, then we know what's going to happen. Okay, so here is probably let's print the current. And what should we say here? The indices or the values? Probably the values. Let's go for values, and that would be list of I1 and list of I2. Let's try to run this. Okay, value to find is 4, searching between 4 and 8. Well, remember, at the first step, we're checking against the middle of the list here, and the middle is going to be here because of the integer division. 4 is less than that, and so we're searching now between 4 and 8 in this part of the list, and the pivotal point is 6 here, and j is 6 is pointing to 6, and then because 4 is still less, then we search between these two, and now the now j is going to be equal 0, and found for it at index 0. So that's fine. Okay. That's fine, and it works. But what didn't work the previous time? Well, last time we thought we would look for 67, the last element. Let's try that. All right, here we get in the loop. So what's going on? Let's see. We need to find 67. We look at this, and 67 is greater than 8, and so the next area that we're looking for is between 8 and 67. We split that in half. J becomes J now starts pointing to 10. We search between this, and so every time we bring up the bound a little bit higher up, but here, whatever we do, j, these are the elements 0, 1, 2, 3, 4, fourth and fifth. So 4 plus 5 integer divided by 2 is still 4, and so the boundary is not updated anymore. So j gets stuck at this next to last element. Well, why is this happening? That's happening because see our notebook is still running. It's happening because we're using integer division, essentially, right? So there is no way to get the index of the last element of the array with integer division. So to get around that, an easy way is to actually just check explicitly if val equals list of the last element, like so, then return length of list -1, the index of that last element. And now it should work. Let's try to... oh, is it now hanging completely? Stop. Stop. Okay, did it add the check? Yes, here's the check. We'll restart the kernel just in case. And run this again. And here we are. The value to find is 67, and we get immediately the answer. Why is that? Well, because we actually stop over here. And for any other value, for example 34, we'll have to go through the steps still. Okay, so I think we're done with that code. Let's run some checks here. So here, what are we doing? Similarly to video 9, we are generating a random list of integer numbers. We sort them, and they are of a particular size, right? And then we randomly choose the index of the number that we want to look for, right? So here we're giving the value, not the index key not. And here's how the program works. We need to find 31. 31 is here. So first we are looking at the whole list, split it in half, and immediately start searching in the lower half. Then split this one in half, and we're searching within this region. And then 31 appears to be right in the middle of this region, and so we're lucky we get 5. Let's do it again with the longer list maybe. Here we are, a longer list. We are searching for 88. We're splitting it in the middle here, and immediately start looking at the upper half of the list. And then on the next step, we're splitting this upper half yet again into halves, and we're looking at the upper half again because 88 is greater than 78. But it is now below the middle of this region, and so we're searching between 78 and 90 and get it at the fourth step. As you can see, we only need an additional step compared to the previous case, if I'm not mistaken, right? So let's increase the list by another 10 elements, and here we need 1, 2, 3, 4, 5 steps, and we're looking for the zero which is in the first place. How about 50? We're looking for 93, and we need 1, 2, 3, 4, 5 steps. So as you can see, I'm increasing the length of the list, but the number of steps needed to find the number doesn't seem to be increasing all that much. And this is the virtue of all of the divide and conquer algorithms, which are typically have the complexity of big O of log n. So this is my previous implementation, what I've written before. You can see here I'm checking actually both for the beginning of the list and the end of the list. And the reason for that is that in the beginning, even though we are finding the first element in the list, if we need to find it, it takes actually the maximum number of steps. So, including an additional check here for the beginning of the list might actually make sense as well. Okay, that concludes this video. You can read a little bit more about divide and conquer algorithms in this blog post. See you next time.